Hello, welcome to Lab 3 for Physics 2211, where we review the main concepts behind momentum's principle through the study and analysis of the interactions between a black hole, a spaceship, and a star. The main objectives behind this lab are to determine the mass of a black hole by finding the net force of a star orbiting around it, and to determine the initial velocity a spaceship must have to get as close as possible to a black hole without being sucked into it. Before going to the results of this experiment, let's go through the fundamentals. So we always start off by Newton's second law of motion, which we know states that the final velocity of an object equals its initial velocity plus the net force divided by the mass multiplied by the change in time. If this equation is rearranged into the multiplication of the mass times the change in velocity over the change in time equals the net force, we get the momentum principle, which can also be denoted as dp over dt. We also know that a vector can be expressed as a multiplication between its magnitude times its direction. And if this is applied the product rule differentiation, we get the perpendicular and the parallel components of our net force. The parallel component equals the change in the magnitude over time times the direction, and the perpendicular component equals the change in the direction over time times the magnitude. We can also apply Newton's universal law of gravitation, which equals the gravitational constant times the multiplication of the mass of the two objects that we're studying over the magnitude of the distance between these two objects squared multiplied by the direction. All of these components will allow us to get to the mass of the black hole, which is the main objective of this experiment. Starting off with the computational model, as you can see in the image, we have the starter code provided, which was edited in order to get the desired trajectory. The lines edited were the mass of the star and the time interval between the imported data points. The mass of the star was given, and the change in time, we used 86,400 seconds, which corresponds to the seconds in a day. Going further into our code, we have our while loop, which will run as many times as necessary for the star to orbit around the black hole. So, as you can see, I'm circling down the most important sections in which were the major edits were done, starting off with the changes in momentum, changes in velocity, and the section is in which we calculated the parallel components and perpendicular components of our net force. On the second image, we can see that in order to get the mass of a black hole, we had to rearrange Newton's law of universal gravitation. We also included in line 197 and 198 the necessary parts of code needed to add up all of the masses calculated in each while loop, and then take the average of these masses to calculate an overall mass that will give us the mass of the black hole. Once all the necessary edits were done in our code, we ran the program, and we obtained the main results that you can see on screen. The most important one, I would say, will be the black hole's mass, which we'll use in the next section of this experiment. In this portion of the lab, we'll be sharing the results for determining the spaceship's velocity to orbit or get as close as possible to the black hole without being sucked by it. Just as we did before, we edited the main lines of a started code provided in order to get the speed of the spaceship. In lines 56 and 57, we inputted the desired speed that we wanted for our ship. In my case, I used the same line for the planet speed. I just changed the magnitude for that of the ship. On the second screenshot, we have the main lines of code that were edited in order to get the gravitational force acting on the planet and acting on the ship. Once we obtain the net force as total, we use this to calculate through Newton's second law of motion the new velocity and the new position that will make the planet and the spaceship move. In these two videos, we can see the motion of our planet and spaceship. As you can see, the planet keeps orbiting around the black hole, whereas the spaceship goes out of orbit, but it gets as close as it can to the black hole, which means that the initial estimate for our spaceship's velocity was enough to get it as close as possible to the black hole. Finally, we come to the conclusions of the experiment. What does it mean and what if? So, what is the main difference between the net force, its components, and the momentum and its components? Mathematically, there is no difference. Momentum is just a calculation when we know the velocity, the mass, and time of the system, whereas net force we calculate it when we know the mass of the systems and the object. Nonetheless, we already noticed that the change in our momentum equals our net force. So that means that it is basically the same objective, just that the momentum is being multiplied by the mass. Also, what if we wanted the spaceship to orbit around the black hole just as the planet did? In this case, we would need to take into consideration the gravitational force that the spaceship is receiving from the black hole, which would have to be the same that the planet is receiving in order to stay on orbit. I hope this lab was useful and allowed you to understand the momentum principle and how to study the parallel components and the perpendicular components of the same. Thank you.